গুড ইভিনিং সবাইকে। ধন্যবাদ আমাদের সাথে আজকে যুক্ত হওয়ার জন্য। ক্যাম্পাসের একটি অন্যান্য কার্যক্রমের সাথে একটি নিয়মিত আয়োজন হচ্ছে ক্যাম্পটক, যেখানে আমরা অ্যাস্ট্রোনমি এবং রিসার্চ বিষয়ক বিভিন্ন গুরুত্বপূর্ণ বিষয় নিয়ে আলোচনা করে থাকি। আজকে আমাদের 10ম ক্যাম্পটকে যুক্ত আছেন ডক্টর তাবাসসুম শাহরিয়ার তানভীর। তানভীর ভাইকে ধন্যবাদ আমাদের সাথে যুক্ত হওয়ার জন্য। আমি আজকে ক্যামের টপিক হচ্ছে স্টেলার ইনিশিয়াল মাস ফাংশন। তো আমি প্রথমে আমার পরিচয় দিচ্ছি। আমি মিউ আক্তার মায়া, আজকে হোস্ট হিসেবে আছি এই ক্যাম্পটকে। আমি পদার্থবিজ্ঞান দ্বিতীয় বর্ষে পড়াশোনা করছি শাহজালাল বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয়ে। ক্যাম্পাসের অ্যাসিস্ট্যান্ট জেনারেল সেক্রেটারি হিসেবে কর্মরত কাজ করছি। তো আমাদের সাথে আছে কো-হোস্ট প্রত্যাশা।
হ্যালো সবাইকে, আমি আজকে ক্যাম্পটকের কো-হোস্ট হিসেবে আছি। আমি পড়াশোনা করছি শাহজালাল বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয়ের জিওগ্রাফি অ্যান্ড এনভায়রনমেন্ট বিভাগে, এবং আমি বর্তমানে ক্যাম্প-সাস্টের 12th কমিটির স্টাডি সার্কেল সেক্রেটারি হিসেবে আছি।
ধন্যবাদ প্রত্যাশাকে। আজকে ক্যাম্পটকে আমরা দুটি সেগমেন্টে ভাগ করছি। প্রথম সেগমেন্টে তানভীর ভাই একটি প্রেজেন্টেশন দিবেন এবং দ্বিতীয় সেগমেন্টে প্রশ্নোত্তর পর্ব থাকবে। আপনাদের কোনো প্রশ্ন থাকলে আপনারা সেটা লাইভের কমেন্ট সেকশনে গিয়ে বলতে পারেন এবং আপনাদের সবার প্রশ্নের উত্তর দেওয়ার চেষ্টা করা হবে। তো এই পর্যায়ে আমি তানভীর ভাইকে অনুরোধ করব তার শুরু করার জন্য।
Hi guys, thanks for having me. It's really good to start the new year with a topic that's very near and dear to me, which is the stellar initial mass function. So yeah, without further ado, let's start actually. Okay, so today we will be talking about a few things. One of the things, so we will cover a variety of things within the stellar initial mass function. The outline of the talk is basically we'll go through what is the IMF, the relationship between star formation and the IMF, IMF observations, a theory, also what the environmental variations are of the IMF, and summary and open questions, mostly the end. So, what is the IMF? The IMF is basically called the stellar initial mass function that describes how newly formed stars in a given region are distributed by mass. This serves as a fundamental blueprint for star formation for a myriad of reasons. On a star formation factor, you can think of it as this way, that through IMF, we know in a region how many low mass stars are there and also how many high mass stars are there. That's one thing, but as you know, stars play a huge role in how galaxies evolve in the end, and that's how the IMF plays a huge role in terms of galaxy evolution, because it's not only influences luminosities, it also influences chemical enrichment in galaxies and how feedback process works. And also, the IMF is an important tool in terms of understanding how many planet hosting stars might be within a region, depending on how many low mass stars it forms. So yeah, IMF plays a huge role, but still to this day remains one of the biggest puzzles in star formation, and also because of its shape and what kind of physical processes drives it. So before we talk about the forms of the IMF, I want to talk a little bit about star formation essentials for understanding the IMF. So as we all know, stars are born in giant molecular clouds. So basically these are giant clouds of gas and dust, where your due to gravitational instability gas form. So this is a nice movie of a molecular cloud in terms of how stars form. The movie is from the Starforge collaboration, and it's taken from one of my colleagues there. So basically, this is a turbulent gas cloud, and you can see like under the influence of gravitational instability, um, and of course with also turbulence, this cloud will slowly start to fragment and will break into multiple dense cores, and those dense cores will then break apart, will then collapse and start to form stars. And as you can see, like some of the stars are forming around here and here. You can see these stars are forming. So basically this region have collapsed and formed stars in the end. But as you know, as soon as stars form, the feedback processes began, such as stellar winds, radiation from accretion heating, protostellar outflows. As you can see, these stars have started to uh, shoot out powerful jets out of this, which is also which can influence how molecular cloud acts in the end. And also, if a star grows too big, it will become supernova. So supernova explosions also can impact how the star formation will act like within of regions. It will also impact what kind of final mass distribution you get. So this is so talking about this is the reason because turbulence and feedback process do directly shape the IMF, because it influences how cores are formed and how much mass they can accumulate. Uh, so forms of the IMF. So the first person who derived the form of an IMF was Solpeter in 1955. Uh, so he counted the solar neighborhood stars and described the IMF as a pure power law distribution. So this is to this day, like even after like 60 odd years, it's still true for stars that's like greater than one solar mass. So basically, if stars are bigger than the sun, this power law distribution holds true. But if you go lower and lower into the masses, there is a break point, obviously, and which the power law can't derive because of as you can see that the power law is just a scale-free thing. So scale-free distribution. So therefore, Miller and Scaler in '79 introduced a log normal distribution with power law tail and
এক্সকিউজ মি ভাই, একটু ইন্টারাপ্ট করছি। আচ্ছা, এই যে স্লাইড গুলো কি মানে একটার পরে আরেকটা আসতেছে? কারণ একজন বলতেছে যে হচ্ছে দেখা যাচ্ছে না ঠিক মতো।
uh, really. Let me see. এখন is this good?
এখন হ্যাঁ, এখন আসতেছে। জি।
So let me know. If I do this and I go back and forth, does this work?
হ্যাঁ, এখন ঠিক আছে।
Okay, good. Going back to the talk again. So Miller and Scalo introduced a log normal distribution to try to explain the peak of the IMF and the low mass. Um, and since then, quite a few people have tried to propose different forms of the IMF. The more common ones are the Kruper's broken power law IMF, or the Chaubrier's combination of log normal and power law IMF. So, wanna right now I want to basically divide the talk into two phases. One will talk about IMF observations. Here I will give a brief sort of idea of how IMF is observed in different star forming regions. So one of the general considerations is that you have to divide it in two things like resolved versus unresolved, and within resolved you can do the field IMF and the cluster IMF, and why I'll get to that in a bit. So resolved star population, you can just basically count the stars in this case. In a way, basically, this is the stars that you can like observationally resolve. So I'll talk about the IMF in the field and the IMF in star clusters. Unresolved population is basically like once we cross the threshold of the local universe, say, in a way, like you can't resolve stars when you go beyond a few MPCs per se. Like if you want to say, I want to observe the IMF of a really old galaxy, but that galaxy is like, I don't know, 20, 30, well, 10 MPC away, give or take. If that's the case, you will never be able to resolve the stars there because, well, we don't have the capability yet, even with JWST. So you have to adopt different models for that. So that one of the models is called the spectral feature models for passive galaxies, and the other one is mass to light ratio. And we'll get to those as well. So the field IMF is basically uh, for lower mass objects. So it's basically for stars that's lifetime is greater than 10 gigayears uh, compared to the age of the galaxy. So this is the best statistics. Like if you want to do try to calculate the IMF for a whole galactic field, this is like field IMF is one of the best place, like one of the best way to do it, and you can have like samples greater than 10 to the power 6 in terms of like how many stellar population you can accumulate. So one thing is, if you want to do like if you have this large of a data set, then doing spectroscopy is quite expensive. So especially for dim targets, because the closer you are, it's easier to observe this. But if you're like lower mass stars tend to be quite dim, so if you're like also further away, then it gets a bit difficult to do spectroscopy. Then what you do is you take photometric data out of those. So there are a few steps if you want to calculate a field IMF. One is you got to calculate the luminosity functions and color distributions. And once you have that, you can also use um, distance estimates from parallax. It's been possible to get accurate distance estimates from ever since Gaia came online, and the data sets have been available to public. So with that, you can also, from those distance estimates to color, you can also get luminosity functions, and then you have to correct for biases, the extinction bias, the Malmquist bias, and metallicity bias. I'm not going into too much detail of those because that will just take a whole talk just to talk about these things. Then you have to correct for unresolved binaries, and like the unresolved binaries are probably one of the biggest factors when it comes to calculating IMF in the galactic field, because you can't resolve binaries as well up, like when you go out further, and that can also cause some kind of uncertainties in your IMF. And obviously, once you have all this, you can then correct the luminosity functions and you can convert it to mass distribution. So this is a plot that's taken from Solimer 2019, where he basically tried to calculate the field IMF out of, I don't know, give or take 120,000 stars. So these are two different settings basically. So on the left you have the mass functions that's derived using assumed unresolved binary fractions. So he assumed how many binary fractions would be within that uh, stellar population range, and he tried to calculate what kind of what the mass functions would look like on the left hand side. And on the right hand side, it's basically he created three different mass magnitude relations and
Uh,
then like basically calculated the IMF there. And the interesting thing is the IMF peaks at around between point 0.1 and point 0.3 in these cases. So that shows the IMF is, so that
হ্যাঁ,
shows the, yeah,
আহ, আচ্ছা, আমার মনে হয় এখনো ওই যে স্লাইড, এই যে এখন চেঞ্জ হয়েছে এই পর্যন্ত ফর্মস অফ আইএমএফ, ওই যে ওই স্লাইডটাই ছিল।
okay.
ম্যানুয়ালি করলে ভালো হয় আমার মনে হয়, হবে আর কি ওটা।
Okay. Right. So the so there is that. And is this better now?
জি,
Is this better?
হ্যাঁ এখন চেঞ্জ হয়েছে,
Okay.
ম্যানুয়ালি করলে বেটার।
Acha, ঠিক আছে. So IMF in young clusters. So we were talking about field IMF before. The field IMF is good to do lower mass objects, and you can get sort of a feel of what the IMF is like in the lower mass end, but you can't do higher mass objects there. So therefore, because and the reason behind it is higher mass objects live for so little time compared to lower mass objects which lives for billions of years. Compared to that, high mass stars mostly live up to a few million years, give or take, and then they, you know, explode most of the time. So that's why we try to measure the IMF in young clusters, because this is the only way to probe the IMF of stars greater than a few solar masses. And another advantage of studying IMF in the young clusters is the metallicity is almost uniform in every way. So it reduces the bias. And also you'll have less dust, or the dust is more uniform there. And also the distance within, if you want to study IMF in a cluster, is probably the same, whichever way you go. And another advantage is also your low mass stars or brown dwarfs are brighter when young. So you can even go into lower masses. So one of the disadvantage is it probably has a much worse statistics. Like in field IMF, you can go up to 10 to the 6 stars, or 10 to the 7, give or take how many stars you're counting. But here, if you're doing it in a cluster, then you're limited to how many stars are there, between like 10 to 3 times of 4, probably. Um, Also, the low mass stars will be pre-main sequence, so they haven't entered the main sequence yet. So you'll probably have more uncertain mass magnitude relations regarding that, and also you'll have different extinctions due to dust within the cluster. So you'll have like different extinctions of dust in different regions, and also there is a possibility of dynamical ejections as well. So the Orion Nebula cluster is probably the closest place from the sun where we can study the IMF, which can be extended up to masses significantly larger than one solar mass. So this plot is taken from Gennaro and Roberto from 2020, where they looked at the ONC IMF for different assumed star formation histories in the region, and given it different functional forms. And as you can see, like even if they have given it like different sort of star formation history, as you can see, like it follows more or less. It peaks around it more or less at the same region. Um, and one of the reason for picking ONC is because the population is relatively young, and also the Lerma stars are at their brightest stage. And quite a few studies have been done other than Gennaro and Roberto, like Hillenbrand 97 and Gennaro 2010. These are like one of the few I can mention. They have found that the peak of the IMF is around zero point 0.2 and zero point 0.3. So this is, so here we're talking about the IMFs within, like basically in the local universe, basically Milky Way and nearby galaxies. where you can actually resolve the stellar population. So the field and the cluster IMF are two different star forming regions, and both are telling us that it's peaking around zero point 0.2 to zero point 0.3 solar mass. Uh, so that led to some reviews of what the IMF would look like in the local universe. So this plot is taken from Bastian's review in 2010, where they looked at uh, the IMF in the local universe. And this is a compilation of different star forming regions. So it starts with your open clusters to global clusters to field stars and dense clusters. Like you name it, the kind of stellar environments it has it. And the interesting part here is this shaded region here, which is where the IMF is peaking at. And as you can see, it's more or less in agreement with each other despite their uh, different star forming environments. Like, so it tells us that the IMF is more or less universal in our local universe, which is quite an interesting fact. So, but that's where we can resolve stars. But what about regions where we cannot resolve stars? What does the IMF look like? So, right now we can no longer count stars to, you know, talk about what the IMF looks like. So, one of the ways you can uh, calculate the IMF in unresolved population is by a method called the integrated light spectroscopy. So this method targets old ellipticals, galaxies that have long gone through the star formation process, and where you can, yeah, this is the place where you can do this. You can use this kind of method to find out what the IMF is like. Uh, so one way to do this, it's like to use gravity sensitive lights like the sodium 1 doublet or the FEH, the iron hydrogen Wingford separates Wingford lines. So the way it works is basically you can use these lines to sort of separate uh, like dwarf stars from giants, because these lines are more prevalent in dwarf stars than giant stars. So this way you can sort of differentiate your lower mass stars to higher mass stars. So so if you look at the top panel of this, you can see that the K giant, which is basically your which is a giant star and M giant star, they have like one sort of lines. But if you look at the M dwarf, it has a different sort of spectra compared to the giant. And we can then use this sort of spectra as baselines to differentiate like dwarf stars to, say, giant stars. And it's true for the Wingford spectral region as well. Like your M dwarf gives a different spectra compared to your giant spectra, which is more or less static compared to it's more a bit wobbly. So a lot of people have done these studies to find out the IMF in ellipticals. Interesting papers were the Van Dokkum and Conroy paper in 2010, where actually found they used this method and they found that the IMF is more bottom heavy rather than universal. So that means there are more lower mass objects within that galaxy than basically your like local universe IMF. So the IMF may not be universal in if you go out to like more extreme star forming environments like old ellipticals. So that's like one way to do it. Now we're talking about another method of doing the IMF, which is the mass to light ratio. It's also an interesting way of measuring it because what you're doing is you're just measuring the ratio of mass to luminosity in some broadband. For galaxy where you cannot resolve stellar population, and then you compare the mass to light ratio to a predicted value for a given IMF. For example, you can assume that you can assume a Schrodinger IMF, and you can then calculate the mass to light ratio by like sort of calculating the luminosity of the stars in a Schrodinger IMF distribution, and then you'll have the mass to light ratio from, say, elliptical galaxy, right? And then you can compare whether the mass light ratio of the elliptical galaxy is bigger than or smaller than the mass light ratio that you get from a given IMF. Uh, and if it's greater than one, then you know it's bottom heavy, so there are more lower mass objects there. If it's less than one, then you know it's bottom light, so that means there is less lower mass objects. Um, so mass light ratio, an interesting thing. Quite a few studies have been done using this method. The True 2010 used lensing and kinematic methods for 56 early type galaxies, and early type galaxies are basically our giant old galaxies, and then an interest found an alpha of 2. So what is an alpha? So alpha is known as the mismatch parameter. So basically, in this case, we're saying, like, see how we were comparing the mass to light ratio of a given early type galaxies to the mass to light ratio of a given IMF. So you take an IMF and then you compare it with the mass light ratio of the galaxy. So that parameter is called the IMF mismatch parameter, which also known as alpha. And that basically is how you can like sort of create calculate that mismatch parameter for a given galaxy, and then you try to plot it against velocity dispersion, and you end up seeing a bottom heavy IMF. So this paper, this plot basically here is taken from Gu et al. 2022. So they had their own set of early type galaxies, and then they basically also had galaxies from other studies like the Capillary 2012, where they looked at 260 early type galaxies. They also had like True et al.'s paper, also the Newman paper, and they stacked it, the velocity dispersion with like alpha. And the interesting part is as your velocity dispersion increases, which basically is leading to more and more giant elliptical galaxies. You can see the IMF mismatch parameter is also increasing. It's like bigger than the given IMF. So these dashed lines here are the what the mismatch parameter would look like for standard IMFs like a Krupp or Salpeter. And as you can see, these are higher than that, which basically tells you that the IMF is more bottom heavy in early type galaxies. And yeah, that tells you that the IMF may not be universal, really, once you get out of the local universe. So the summary of observations of the IMF is basically studies measure stellar masses in nearby clusters, giving direct IMF constraints, but also it's limited to local volumes. Unresolved method uses sort of integrated light spectroscopy, lensing, or kinematics to derive mass to light ratios and then probe distant IMFs. So the IMF is definitely near universal in the local universe. It's more bottom heavy. It's been found in early type galaxies. So, as we have already told, how IMF variation affects feedback, chemical enrichment, and overall galaxy luminosity. So, in a way, it's really the basically having a more accurate IMF is more important to try to understand how to model galaxies accurately across cosmic time. So the open question then becomes like, what physical forces drives the IMF variations. And that's where theory comes in. So we're going to talk about a little bit about the IMF theory. So a brief overview is the central puzzle is, as we've talked about earlier, it's definitely identifying the physical processes that fix the overall shape of the IMF. A unified theoretical model would definitely account for the parallel tail of the high mass end and the low mass peak. And there have been a lot of studies that tackle different aspects of the IMF theoretically, but not a single study or theory has been provided so far that is a definitive explanation for the shape of the IMF or can predict the IMF in different galactic environments. So what we know so far is that the IMF is nearly universal, right? So in the local universe, if that's the case, the near universal IMF in the local universe, then you need a simple physics that can uh, basically explain the near universality of the IMF in local universe. And isothermal turbulence then becomes a key driver. So quite a few studies so far have been trying to model the IMF using the properties of turbulence. Here are three more famous ones. One is the Padwan and Nordland study in '02, where they emphasized the isothermal supersonic turbulence to explain the high mass slope. However, well, their model does not produce a sharply defined low mass turnover. And why is that? We'll get to that in a minute. The Hannibal and Chaubrier study, they still used an isothermal model, but right this time they introduced a spatial density structure so that they can better capture the low mass turnover in the IMF. And lastly, the Hopkins 2012 study, where he used a refined excursion set formalism, so which is basically sort of an update on the Schechter type approach of Hannibal and Chaubrier. And also, they did that under different isothermal assumptions, and they also recovered a salpeter-like IMF, which is a power law. So this is where the limit of the isothermal model comes in. Because in purely isothermal conditions, if you think about it, you're continually producing purely power law distributions, and power law distributions are scale free. So even if you rescale these simulations, you will end up uh, having the same IMF distribution, which will not have a natural peak in the low mass end, because you need sort of artificial uh, initial conditions. So you need to uh, sort of, the way you get the peak in an isothermal simulation is if you have artificially set where your density would break, because what would happen is in an ideal isothermal situation, your gas will continue to fragment up until very lower to low and low and low masses, because there is no kind of physics there which can, in a way, arrest the fragmentation process. So this is a plot that's taken from the Gisani 2020 paper. So also one of the co-founders of the Starforge project. So the left is a surface density map of isothermal gas, isothermal giant molecular cloud at 6.1 megayears. So just to clarify, meg and gigi is that I'm talking about, these are millions and billions of years, but in at least in theoretical astro, we do just talk about it as mega and giga because it's just probably easier that way. Well, I don't know. Don't ask me. That's how I've been told. Uh, so, so yes, it's 6.1 megayears. So if you look at the scales here, it goes from like around, it starts at 50 parsec and then it goes down to like about 30 AU. So it shows the gas density, like the resolved gas density in the Starforge setting, and the blue dots here are the stars that have formed within uh, this in this molecular cloud, and the right hand side is the mass. The IMF basically that came out when we used different mass resolution for this same giant molecular cloud, as you can see, and this is what I'm talking about. The parallel tail is more or less like unaffected here, but if you go into sort of lower and lower mass, and as you can see, like simulation is like breaking into more and more into the lower mass territory, so, which kind of is proving the point correct. Like in an isothermal setting, you're you're probably breaking in fragment into more and more lower mass objects. So this is where this kind of modeling sort of fails, because as much as it is telling us that it can resolve the high mass tail, but it's not resolving the low mass end. So any viable theory of the non-polar IMF, low mass IMF, then does require a deviation from the isothermal gas. So how do we achieve that? So we basically need to stop the fragmentation of gas. So the way we do it is we change the equations of state we have in our simulations. One way to do it is that we stiffen the equations of state. So basically, at a certain density, we basically stiffen the equation of state so that the fragmentation halts there. So that gives you sort of the observed IMF turnover, but again, it's very sensitive to initial conditions. So basically, what we need is sort of a mechanism that can that can give you the shape of the IMF in a way that's not uh, where it's not sensitive to the initial conditions. And for that, radiation feedback has been proposed as a potential mechanism. So what happens is young stars form and then they start to heat up the gas around them. And we have seen from studies that fragmentation is strongly affected by the temperature structure of the collapsing gas. And radiation feedback does suppress fragmentation by raising the temperature. But how effective your radiation feedback is completely dependent on your the surface density of the star forming region. So the summary of in terms of theory is basically your isothermal turbulence models do reproduce a saltpeter-like slope, but it struggles to create a consistent low mass peak. So small departures from isothermality can set the IMF mass scale, but again, very strongly dependent on the initial conditions. Radiation feedback do raise gas temperatures. By this, they suppress fragmentation, and then this way they create a characteristic mass. So surface density, metallicity, and magnetic fields can shape how feedback, uh, how strong the feedback is, basically. So we need to have a look into it. So this is where I did a bunch of experiments or simulations to try to understand how different environments along with feedback can affect the IMF shape. So the first, we're talking about the environmental variations here. So we'll talk about the surface density first. The aim is basically to examine how surface density along with feedback can affect cloud fragmentation and stellar mass functions. So what we did was we ran a series of simulations where the dimensionless parameters are constant. So what are the dimensionless parameter? I'll try to explain them in a bit. So it's your Mach number, your alpha Mach number, your Fourier ratio, just to name a few of the more important dimensionless parameters. So Fourier ratio is basically dictates how strongly your molecular cloud or your star forming region is gravitationally bound. So the more gravitationally bound it is, it will probably form more stars. If it's no more gravitationally bound, then the gas will basically spread around and you will not form much stars. Um, your Mach number is basically the strength of your turbulence within that star forming region, and your alpha Mach. That tells you how strong magnetic fields are really. So basically, it's a clever way of like setting the simulations, because if I don't have any kind of radiation at all in my simulation, what will happen is the simulation will basically just be rescaled versions of one another. So what breaks the symmetry between all the simulations are the feedback mechanisms. So so this way we can understand how really radiation, along with different surface densities here, can impact the shape of the IMF. And here in these studies, I'm only interested in understanding the low mass end of the IMF, what the IMF peak is. I'm not interested in the high mass end. So yeah. So how did we set up the simulations? So we set up the simulations. So we did six different cases, three cases with different initial surface densities, times random realizations of turbulence for each case. So uh, you can do like turbulent seeding within a large scale simulation, and you can randomize that as to how your turbulent velocity field will generate. And we did two of those, and we combined it with three different cases of initial surface densities. Uh, so we ran the simulation up to a fixed SFE of 5%. So you get asked like, what is SFE? So SFE is basically star formation efficiency within a star forming region, because not all of your gas gets to be made into stars because of these different feedbacks and like turbulence and other factors. About like 1 to 10% of your gas is made into stars. So star formation is a very inefficient process to begin with. So we ran the simulation up to a fixed star formation efficiency of 5%. So essentially, your star formation efficiency is uh, the total mass of the star is divided by the total mass of the gas, and then you get like what percentage of the gas was turned into stars. So this tiny table here is basically tells you the initial parameters of the simulations. So as you can see, this here is what the masses within those boxes are that we simulations ran for. It goes from 500 to 2000 solar masses. These names are here is basically element H. So element H basically are named after the three different surface densities that we did. So we did a low surface density region where your box is bigger and you're holding a bit more mass, but the density is lower. And the H here is the high surface density run, where again, you're basically, you have more initial density, gas density within that simulation box. So this is basically a nice little movie of the simulations as how they worked. So before I play the movie, I want to explain what the top and the bottom panels are. So the bottom panel is the temperature distribution, and the top panel is the gas distribution within that star forming region. And as you can see, the gas has already sort of created these filamentary structures here. Um, and interesting, and these filamentary structures have been formed when you drive turbulence within that box. So once you once you drive turbulence within that box, basically the gas forms sort of a filamentary shapes, and this is like the densest region within that star forming box, where you will end up creating stars. As you can see, like the stars are forming uh, within that filamentary regions as the simulation progresses. Um, and an interesting thing on the top panel, you can see as the simulation progresses, these filamentary structures are getting becoming more broader as your surface density increases, and more disruptive as well. And if you look at the bottom panel, uh, uh, what you can see is here it's more luminous than these two regions. And that is because in high surface density regions, your stars are more efficient in trapping uh, radiation feedback. So it lights up the surrounding gas more, the stars, compared to uh, the other two simulation boxes. So yeah, and why is that? We'll get to it as well. So what does the star formation rate looks like here? So on the left side, you have how long it took the simulations to reach 5% star formation efficiency. To the right side, where I showed how many stars you have formed within the 5% star formation efficiency. So let me try to explain the bottom panel here, which is time normalized. So the way time has been normalized is that you take the time of the simulation minus the time when the first star was formed in the simulation, and you divide by the free fall time of the box. So obviously a question you can ask is, what is a free fall time? So basically free fall time is when all of your gas will collapse, and it will start forming stars. So that comes from the free fall time comes from Jeans criterion. Uh, we will try to explain it in the Q&A part if anyone has any questions on the Jeans uh, criterion bit. So the interesting thing here is that the dashed and the solid lines, obviously. So the solid lines are one set of turbulent realizations, and the dashed lines are a different set of turbulent realization. And in the solid cases, you can see that they have reached sort of 5% star formation efficiency relatively around the same time, both low, medium, and high surface density runs. But in a different turbulent realizations, that's not the case. Like the low run have reached, it has taken the longest time to reach 5% star formation efficiency compared to the high surface density run, which has taken the least. Um, and in terms of how many number of stars they have formed, the low mass run has produced more stars compared to the high surface density runs, which is the blue stars in both realization cases. Uh, so yeah, there is that, and why is that? We'll get to it as well. So what does the mass distribution looks like? So this is a cumulative distribution function plot. So this is similar to, like, if you guys have done stat, it's like a PDF, but where you do probability distribution functions. This is where you do cumulative, and these are two. So I'm trying to show the mass distribution in two different scales. Here, the left-hand side is the absolute stellar mass. which is you're taking the stellar mass as it is in this case in solar mass units. But this distribution here is m star by m box. So basically, it's where I have normalized the mass, and by normalizing the mass, it's easier to compare apples to apples. Basically, now you can compare all three simulations mm, more accurately to try and understand how the IMF of these three different boxes have evolved. So this is taken at 5% SFE, obviously. So first, if you look at the left-hand side, you can see it goes from black to red to blue, and as you can see, the median value decreases. So by median value decreases, by that I mean the 50 percentile value in all these runs have decreased as your surface density have increased. Um, but if you look at the right-hand side, especially the green line here. So the green line here is basically a run where we do not have any kind of feedback mechanisms involved. And if there was no radiation feedback, all these three red, black, and blue lines would end up be rescaled versions of this green line here. So the green line is basically trying to show how feedback has affected these runs. And if you look at the right hand side plot, you can see that here the left, the black line, which is the low surface density runs, has more higher mass objects than the blue line, which is the high surface density run. But the high surface density run also has a higher threshold for lower mass, higher threshold for fragmentation suppression compared to the black line here. And why is that? So why is that is the best way to explain it to you be how basically radiation feedback is impacting your mass distribution on both ends, right? So first we'll talk about how radiation feedback is affecting. This plot here is basically a 2D phased plot of the gas temperature, of the how the density and temperature of the gas within the within the box, and you go from L to H, obviously. So low to high, you're going again, and as you can see that at 5%, like your temperature's higher in the high surface density run compared to the low surface density run, and that is because, like I said here, that you're trapping uh, the radiation more effectively in this region, right? So you're more luminous here. And so that tells us that your high surface density runs are more effective in trapping the radiation more effectively. That way, it is more effective in suppressing fragmentation into lower mass objects. So if that was the case, then you would see more higher mass objects forming in the high surface density runs. But if we go to the mass distribution again, you will see that the high surface density run does not produce more massive objects than the low surface density runs. Rather, it also doesn't form that many, doesn't also go down to more lower mass objects like the low mass run. So it ends up having a more truncated and more narrow IMF compared to the low surface density run. And that is because how protostell outflows are affecting. So when I talked about we included radiation feedback and surface density, we did uh, like heating and protostell outflows from the star. So basically, young star shoots jets from within, and they can also impact how much masses your star formation region. Basically, how much masses your stars can accumulate And in the higher surface density run, in this case, you're breaking the gas more, and therefore you're not producing enough massive stars. So how do we quantify how outflows are affecting? Like in the radiation feedback case, I showed you the density temperature distribution of the gas mass, and you've already seen how the temperature was higher in the high surface density run, so it stops the fragmentation of the gas. So in order to do outflow feedback, what we did is we calculated the surface escape speed of the stars, because the surface escape speed is directly linked to the outflow, like how outflow will behave within that region. At least that's how we developed our outflow code to be. So that's the reason it's easier when you can do like surface escape speed compared to the star formation efficiency. So again, black and blue are your interesting points. And as you can see, the low surface density run has systematically higher escape speed compared to the blue surface density lines. And that is because if you think in real time, it takes the low surface density run the longest to reach, uh, given star formation efficiency, and therefore it allows its stars to contract more towards main sequence than the high surface density runs. And that way, that's how you end up having a larger uh, escape speed in the low surface density runs compared to the high surface density runs. And you end up having more massive objects, because what will happen is, because having a higher escape speed, your outflows have more kinetic energy, it has more volume. So you basically, from the high density region, you're shooting the outflow at a higher speed, and it just punches a hole into the higher surface speed and then goes into lower density regions where it ends up occupying more volume. But and that way you're forming more massive objects, because it's not really impacting uh, the gas breaking up into more clumps. So you end up forming more massive objects compared to your high surface density runs. So how does our simulation results stack up with observations? So one thing we can get out of our simulation is the mass to light ratio, where this we can use that to compare our results with the mass to light ratio, or the IMF mismatch parameter observed in early type galaxies. Uh, so here is a plot where we have done exactly that. We've compared the mass to light ratio with and the IMF mismatch parameter. So an interesting point here is that the exact values are not of importance. The more important thing is here the kind of shifts it produces, because there is a lot of uncertainty when you're modeling mass to light ratio out of a simulation. And also there's a lot of uncertainty when you're modeling mass to light ratio from observational data as well. So the shifts that it produces are more important than the exact value here. The bottom here, the x-axis here, is the age of the stars from 5 to 10 gig years. Basically, what we did is we took our uh, stars from our simulation and forward modeled them from 5 to 10 gig years, and then we calculated the IMF mismatch parameter here. The yellow band, you may ask, what is that? The yellow band is basically the values of the IMF mismatch parameter that is taken from the Gu et al. Paper. Uh, and as you can see, the low surface density run provided IMF mismatch parameter, and the medium surface density provides mismatch parameter or the mass to light ratio that is more closer to the mass to light ratio that you see in early type galaxies. Uh, so that's one point. That's we're talking about what stuff how surface density does that. So low and high surface density run ends up providing more accurate mass to light ratio that you can compare to early type galaxies. And surface density do have an impact in. So we only did surface density before. Now we're talking about another environmental variation, which is the metallicity. So basically, metallicity is how much metal is present within a star-forming gas. So in astro, if you, I think you've already know this, but anything that is not hydrogen is called a metal compared to what we consider metal in our planet. So yeah, so that's how you do metallicity. So metallicity here is basically the gas to dust ratio. So in the surface density runs, we did solar metallicity. So the metallicity of the gas of the box was exactly of the metallicity you'll find in the sun, which is 1. So here we did 3 different metallicities along with the solar metallicity. We gone up to 1% of solar to 10% to 3 times the solar to try and understand how with different surface density would that impact how would that impact the IMF. So this is the star formation rate versus the number of stars it formed, and as you can see, time wise it doesn't matter what kind of metallicity will have, you'll end up reaching the 5% SFE probably around the same time. It's also you'll probably end up forming more stars if you are solar metallicity compared to if you're 1%. 1% metallicity, but that's about it. There's not a lot of difference there. And then what the distribution looks like. So if you remember in the previous slides, we had all the surface densities is the same because now that we have too many simulations, we decided to divide it into 2 portions. So the left-hand side is the mass distribution of the low surface densities at different metallicities, and the right is medium surface density at different metallicities. We decided to omit the high surface density runs in this case due to how much supercomputing time we had at that time. So we just moved ahead with low and medium surface density runs, as also they produced the more interesting results from the surface density study. So if you look at the density, the mass distribution here, that doesn't matter what your metallicity is, you end up producing a mass distribution that is similar to the solar metallicity. And even if there is a small difference, a very small difference, as you can see, it's not that important. But even if we take that weak variation into account, we can see it's not, the variation is still not as significant as when you have different surface densities stacked up against one another. And if I stack up this plot against this plot, you will see that surface densities, different surface density, and will end up providing the biggest shift in the mass distribution. So that shows that the metallicity does not really impact the mass distribution at all. So how does radiation feedback really impact here? It impacts the impact is not, again, it's not as significant as the surface density, but as you can see, like there are some effect of radiation feedback here, where the more important one is in the more extreme one you can see is the medium surface density at 1% 1% 1% solar metallicity. So this is the bottom panel here. So the way I have designed the plot is the top panel is your low surface density run and bottom panel is your medium surface density run. And 1, 10, 1, and 3 is basically what metallicity was there present compared to the solar metallicity run. As you can see, like there is less high mass. Basically, there is less mass enclosed here, and it's also the temperature is higher. It's because of lower metal content, basically. So your mass to gas, so your gas to dust ratio is low. That gives, so basically you end up being more optically thin here. Because you're more optically thin, your radiation feedback is affecting it more. So you have less sort of high mass objects in the less mass involved in the high density region. So, and also your temperature is higher here. So that's what is. And how does protostatellar outflows affect this? Again, we've taken into account like what the escape speed would look like at different metallicities, and as you can see, it doesn't really make any difference. So in order to understand if the weak variations that we see, how does that compare? So to understand that, we plotted this kinetic energy, the momentum and the volume occupies within the box. And as you can see that the 3 times more metal box has a higher kinetic energy and momentum and volume within its outflows. So technically you would think that it will produce a slightly more top-heavy IMF, because that's what we've seen in the surface density run, that if you have more kinetic energy and momentum, you will probably produce more top-heavy IMF compared to if you don't have, if your kinetic energy momentum is lower. So why is that? So that down is basically down to different cooling rates of the gas, because metallicity once you because at different metallicity your cooling rate is different. So at higher metallicity probably the cooling rate is different than the solar metallicity, so it still ends up producing a more bottom heavy IMF. So what the implications of the mass to light ratio is, again, mass to light ratio is the closest thing we can get out of our simulations to study with mass to light ratio that we find in the early type galaxies. And as you can see, surface density still produces the biggest shifts compared to different metallicities. So this is the preliminary results from new studies that we're doing, where we're changing the variations in magnetic fields. So this is at 1% staff emission efficiency, and we plan to finish it at 5%. And an interesting thing is magnetic fields are producing, early results show that it's producing a shift that is more or less comparable to the shifts that you've seen in differing surface density studies. So we'll know more about it in the coming days. So what's the summary of this section is, so basically, if you do not have any feedback mechanism in these simulations, the relative mass distribution would be identical for all simulations. So what breaks the symmetry is feedback. Radiation feedback do suppress fragmentation to smaller objects as the surface density increases, and the protostatellar outflow feedback in the high density run breaks up the gas more effectively, thus suppressing the formation of massive stars. So combination of both these effects leads to a narrower IMF at higher surface densities. Shifts in IMF with metallicities at a fixed surface density are much smaller than the shifts with various surface densities. So basically, if you vary the surface densities, you produce a shift that's more significant than if you vary metallicities at a given surface density. And these variations in surface densities are more likely to drive changes than the variations in metallicity. And variations in surface density is probably responsible for the IMF variations you see in early type galaxies. So if you have any questions, please feel free to ask. Thank you.
ধন্যবাদ তানভীর ভাইকে এত ইনফরমেটিভ একটা প্রেজেন্টেশনের জন্য। এখন আমরা চলে যাব দ্বিতীয় পর্বে। আমাদের দ্বিতীয় পর্ব প্রশ্নোত্তর পর্ব। আপনারা আপনাদের যাবতীয় প্রশ্নগুলো কমেন্ট সেকশনে জানিয়ে দিবেন। আর প্রশ্নোত্তর পর্বটি পরিচালনার জন্য আমি প্রত্যাশাকে ডেকে নিব।
থ্যাংক ইউ মায়া। আচ্ছা, আমাদের কমেন্ট সেকশনে ইতিমধ্যে অনেকগুলো সুন্দর সুন্দর প্রশ্ন এসেছে। ভাই আমি পড়তেছি কোয়েশ্চেনগুলো। রাফি আদনান ভাই প্রশ্ন করেছেন, ইজ দেয়ার এনি রিলেশন বিটুইন সিএমডি অ্যান্ড আইএমএফ?
Interesting questions. What? I don't think so.
সিএমবি হইতে পারে?
It probably is CMP. I don't think it's CMP. I don't know what CMP is. I don't think so, because that's the cosmic micro background is from the Big Bang, and when Big Bang happened, there was no stars. Stars formed after the Big Bang, so no, there is no relationship between CMB and the IMF. I hope I'm not wrong because I don't know what a CMD is. But yeah, it's probably CMB. So yeah, there is no relation between those two. The IMF basically talks about stars that comes after the Big Bang. So no.
ঠিক আছে ভাই, থ্যাংক ইউ। পরের প্রশ্ন করেছেন তন্ময় ভৌমিক। He said, how does the IMF differ between dwarf galaxies and massive ellipticals? What can these differences tell us about the conditions under which these systems formed?
Oh, really interesting questions. So, the IMF, do you have a difference in dwarf galaxies and massive ellipticals? If you were to look at different observational studies of dwarf galaxies, some claim that the dwarf galaxies have a more top-heavy IMF compared to the massive ellipticals. But I don't think so. I've covered a wide range of metallicities in my studies, from 1% to 3 times. That kind of covers your dwarfs to your massive ellipticals. I have not seen any differences. Even if I take the observational studies sort of as the benchmark, their studies lack, in a way, completeness, because if you go beyond a certain distance, you can't surely say that. So it probably differs. Like dwarf galaxies and the IMF is an exciting field that people are still doing studies, but if I were to take the metallicities of these regions into account, it doesn't really make a difference in compared to the solar metallicities. So these kind of also is an interesting question, that what can these differences tell us about the conditions under which the systems formed? So ellipticals are basically at a point when we're measuring the IMF, where your stars are basically, the star formation cycle is probably ended. So it probably will tell us quite a bit in terms of differences. Uh, yeah, because how feedback essentially acted in the earlier stages. So if you run, so basically you have to take these IMFs into account, and then you backtrace it through. You can like probably input that into a cosmological or galaxy simulations, and that will probably end up giving you sort of an answer of what kind of environments these uh, galaxies were at the beginning. So yeah, but the difference will definitely tell us more. Like right now, I can tell you this is that early type galaxies, basically ellipticals, have higher surface densities than your local universe, like Milky Way. So yeah, there's that.
থ্যাংক ইউ ভাই। আশা করি তন্ময় তার উত্তরটি পেয়েছেন। এবং আমাদের পরের প্রশ্নটি করেছেন রাফি আদনান ভাই। From the model fit diagrams, we can see that the models differ quite a bit. Which one is considered the best? If it is case-based, why it is differing so much?
Right. So the models are different because there are different techniques you need to do to sort of study a specific part of the IMF. So, like for example, if you're only interested in the lower mass objects, you can have to adopt, like if you're doing within the resolved stellar population, then you're doing the field IMF studies, or in unresolved cases, you're doing either integrated light spectroscopies or mass light ratios. There is no best model out there because no one has agreed what the best model is. It's just people use different models to actually account to try to measure the IMF within that region. Like for high mass stars, you can't do it in the field star. If you're doing the galactic field, you won't be able to do high mass objects because there are no high mass objects left to study. So you have to go and do it in the young star clusters, and you got to do it there. And you and if you're doing field stuff, and then that's how you do the lower mass objects because those are like really ancient stars. And if you're talking about unresolved population, then you have like basically your uh, spectroscopy method and your mass light ratio method. That's basically up to how you're what kind of data you have available at that time. Like you can, if you have the spectroscopy data available, then you can fit the data like Venn-Diagram and Conroy did, and sometimes mass light ratio is, well, probably a preferred method. Personally, I think mass light ratio is more, probably gives you more accurate result than spectroscopy, because I've always have doubts regarding spectroscopies, but that's just me. So yeah, but yeah, it's there is no definitive best method there. It is definitely case based, and it's differing so much. Is basically what kind of stellar population you are measuring at that time.
থ্যাংক ইউ ভাই। আচ্ছা, তন্ময় ভৌমিকের আরেকটা প্রশ্ন। In simulations of stars formation, how does the balance between cooling and heating processes supernova impact the SFE in a galaxy?
Right. Don't quite understand the question. So, okay, so wait, similar star motion, how does the balance? Supernova happens when your star basically becomes too big and it just explodes. It can have a lot of impact in the star formation efficiency in a galaxy because, again, it depends on the rate of supernova, basically. So how many supernovas uh, can you get? So, for example, if you have a more top-heavy IMF within a star-forming region, you'll probably have more supernova events going on. Um, that will have, and those supernova events will produce more metals within that region, so you'll become more metal rich. So that might uh, have an impact on how what kind of stars do you form, and also it will probably drive the gas away, so you'll probably halt star formation there as well. But so far, what I've seen, what basically uh, sort of holds star formation efficiency within a region is your photoionization from your massive stars and stellar winds. What supernova events does is basically it injects a lot of metals, but within the nearby region, it probably impacts the star formation efficiency in a more significant manner. It, but it's not kind of not even in a negative way. Sometimes your supernova events can drive shocks into the nearby regions, and that way you can end up producing more stars. It's just depending on what kind of star forming region your supernova is going off, really.
এটা হচ্ছে তন্ময় ভৌমিকের শেষ প্রশ্ন। If IMF variations are tied to environmental conditions influenced through large-scale structure formation, could the IMF, as an indirect probe of dark energy, affects on galaxy evolution?
That is a really interesting question. I have not thought about that. So could be an indirect probe of dark energy. Could be. Although could be a really interesting point. Like I've only thought about how we can accurately study galaxy evolution if we use more accurate IMF variations, because believe it or not, in theoretical world of star formation, in galaxy simulations, we only do like we assume an IMF from the beginning, and we just go with it. So far, I haven't seen a galaxy uh, evolution study that takes into account IMF variations within itself. So no one has done it yet, but that would be a really interesting way to probe dark energy and galaxy evolution, like how the IMF can impact that. But I don't know. Probably my answer is maybe, maybe not. I'm not sure because I have not thought about it. But my answer is probably no.
Okay. আচ্ছা, তারপরে রাফিয়া আদনান ভাইয়ের একটা প্রশ্ন। ও
I think
আচ্ছা,
I've.
এখানে সিএমডি বলতে উনি বুঝিয়েছেন কালার ম্যাগনিটিউড ডায়াগ্রাম।
Oh, okay. Right. Yes, there is a relation between color magnitude diagram and the IMF. Because if you do photometry, then you'll have sort of color magnitude diagram out of that, and out of the color magnitude diagram you can get your luminosity functions, and from luminosity functions then you can get your IMF. So yes, there is a relation between CMD and IMF. Yeah, I would like to apologize for this because I do not have that much experience with observations myself. I'm mostly a theoretical person, so in theory we don't really do a lot of studies, or at least I haven't done a lot of studies on CMDs or photometry and stuff. So my knowledge is very limited in that case.
থ্যাংক ইউ। এবং এটা হচ্ছে আমাদের শেষ প্রশ্ন, রাফি আদনান ভাইয়ের আরেকটা প্রশ্ন। হি said, how do your simulations compare to the recent cosmological simulations?
Right. You can't compare the simulations because my simulations are done at parsec scales. Cosmological simulations are done at megaparsec scales, so you cannot compare apples to apples there. The best way to compare my simulations to cosmological simulations would be you take my simulations and you take the data from my simulations and dump them into a cosmological simulation, and then you run that, and from then you can more accurately compare the two things. In simulations, there is differences in scales, like my scales were parsec scales, so that's just limited to one giant molecular cloud. So basically, I'm simulating a patch within a giant molecular cloud to understand how the IMF varies. Cosmological simulation is you're taking like basically you're simulating the universe, and that is not what I'm doing. So you can't compare these simulations.
ওকে, থ্যাংক ইউ। আচ্ছা, আমি মায়াকে রিকোয়েস্ট করছি
কন্টিনিউ করার জন্য।
ঠিক আছে, আমরা আমাদের ক্যাম্পটকের একদম শেষ পর্যায়ে চলে গেছি। আপনাদের মধ্যে অনেকেই জানতে চেয়েছেন আমাদের অনলাইন মেম্বার রেজিস্ট্রেশন সম্পর্কে। বর্তমানে আমাদের অনলাইন মেম্বার রিক্রুটমেন্টটি বন্ধ আছে। আমরা খুব শীঘ্রই এটি চালু করব। এটার জন্য আপনাদের নিকট অনুরোধ থাকবে যে আমাদের পেজে নিয়মিত আপডেট গুলো দেখার জন্য। আর তানভীর ভাইকে অনেক ধন্যবাদ আমাদের সাথে আজকে যুক্ত হওয়ার জন্য। আমরা আশা করছি ভবিষ্যতে অন্য কোনো টপিকে ক্যাম্পটকে আমরা আপনাকে অতিথি হিসেবে পাবো। আমাদের জেনারেল মেম্বার এবং বাংলাদেশি স্টুডেন্ট যারা অ্যাস্ট্রোনমি নিয়ে খুবই আগ্রহী, তাদের উদ্দেশ্যে যদি আপনার কোনো মেসেজ থাকে প্লিজ।
শিওর। যখন আমি আমার জার্নি শুরু করেছি অ্যাস্ট্রোতে, I had no idea about what path to take, really. So a lot of people where I was at that time helped me a lot. And I want to return, give that back to community in general. So আমার ইচ্ছা হচ্ছে basically to help anyone who wants to do research in astro. My doors are always open. You guys can, I don't know, from the CAM organizers, you can get my email address or something, and more than happy to help out with anyone who wants to do research, who wants to know more about astro, or applying to astro grad schools in general. Whatever you need, like happy to do even workshops as well, that can help spread the astronomy amongst university students to high school students, whatever, because it is an interesting field and there is not enough Bangladeshis. We are a huge country with huge population, but there is not enough of us in astro. So I think there is a lot of potential, untapped potential there. So yeah, if you want to know more about research or anything, just feel free to email, because I'm always looking forward, and I'm also interested in working with fellow Bangladeshi students so that I can teach them whatever I can in astro. So yeah. And thanks for organizing this talk. I've always wanted to give a talk in Bangladesh, so that so that I can share my experiences or the research that I'm doing right now. And yeah, thanks a lot.
আচ্ছা, আশা করি আমাদের জেনারেল মেম্বার এবং বাংলাদেশ স্টুডেন্টদের জন্য এটা খুবই হেল্পফুল হবে এবং তারা যে কোনো প্রয়োজনে আপনাকে অবশ্যই স্মরণ করবে। তো আজকে আমরা এখানে আমাদের ক্যাম্প টক শেষ করছি। গুড নাইট সবাইকে।